We're going to continue chapter 30, induction and inductance, Faraday's laws and Lenz's laws. We're doing problem set. The figure below shows a wire that forms a rectangle, width 20 centimeters, height 30 centimeters, and has a resistance of 5 milliohms. Its interior is split into 3 equal areas with magnetic fields B1, B2, B3. The fields are uniform within each region and directly out of or into the page as indicated. Out of the page, in the page. Figure 30-44b gives the change in the z component of BZ of the 3 fields with time. The vertical axis scale is set for BS equals 4 microteslas. That's at the top here, 4 microteslas. And BD at the bottom is minus 2.5B. It's 2.5 times this 4, which is going to be minus 10. And the horizontal axis scale is set T seconds equals 2.0 seconds. It's 2.0 seconds across. What are the magnitude and direction of the current induced in the wire? Well, we'll answer B right away. We have coming out 4 microteslas and coming out also 2 microteslas, and we got going in a minus 10 microteslas. So we know it's coming, it's going, that the magnitude will be into the page because 6 minus a minus 10 will give us a minus 4 microteslas into the page. So the answer to B is into the page. Now, the 3 sections. So if you look at this figure with the copper ring and the fill into the page, you see that the current is counterclockwise. So the answer to B is that the current will be counterclockwise. Now let's just go back to A. We have 3 sections, and we know that it's a 20 centimeters by 3 centimeters. So let's just multiply and get that area. So that'll be 0.2 meters times 0.3 meters, and that's going to equal to 0.06 meters square. So each one of these sections is equal to 0.02 meters. So I'll just draw it over here. Point 0.02 meters square for each one of these sections. And you know that to have an inductance, you must have something change with time to have an induced EMF. And the slope of this graph is showing you the change in time with B, the magnetic field, changing with time. So we have that requirement. So now the formula that we're going to use induced voltage is going to equal to minus phi, that's d phi, dt. And we know phi is equal to A dot B. Now we know we can bring the area out because it's constant. So we'll just bring the area out of the equation. And we know that we're using the slope of this line for the change in B with respect to time. So we can go from this derivative to just the change in B with respect to the change in time. Okay, let's just put all this together. We have and A is 0.02 for all of the sections. So we can just pull that out of this meter square. We know the time is 2 seconds, so we can put that down here, 2 seconds. And we know the slope, we know that B is equal to 4 here, 4 microteslas, so we just put 4 times 10 to the minus 6 teslas. Here it is 2 microteslas plus 2 times 10 to the minus 6 teslas. And we know this is minus 10 minus 10 times 10 to the minus 6 teslas. That's going to go to 0.02 meters time, a minus 10 from a plus 6 will be a minus 4 times 10 to the minus 6 teslas. That's all divided by T. So when we do the math on this, we're going to have .02 times 4 times 10 to the minus 6. Let's correct that. 0.02 times 4 times 10, shift to the minus 6. And we're going to divide that by 2 seconds. And we get 4 times 10 to the minus 8 volts. Now this problem asks for the current. It wants what is the magnitude and direction of the current. Well, we know that the direction is counterclockwise, and we have 5 milliohms of resistance. So we'll just divide this to get the current. Current is equal to over R. We've computed E, which is 4 times 10 to the minus 8 volts, divided by 5 times 10 to the minus 3 ohms, and that's going to equal Clear this. 4 times 10, shift to the minus 5, divided by 5, and we get 8.0 times 10 to the minus 6 amps. So this is the answer to the problem. What did we do to come with this? First, we took the slopes of all these lines, and this is what they are over 2 seconds. That was our B changing with time, delta B changing with time. We got the area, and since each had the same area, from our formula, we put the area, 0.02 meters squared, and then we solved. And we came up with 4 times 10 to the minus 8 V for volts. Then we noticed that the resistance is 5.0 milliohms. So we computed the current, 5 times 10 to the minus 3rd ohm divided by, the 4 times 10 to the minus 8 volts divided by 5 times 10 to the minus 3 ohms give us 8.0 times 10 to the minus 6 amps. So that's that problem.